Today, lesson 50B, linear relationships. That's been our focus so far, is on proportional relationships. And a proportional relationship, of course, leads to a linear graph. Well, we also have linear graphs, or in this case, linear relationships, that aren't proportional. And I've been throwing them in once in a while towards the end of a lesson just to see if we could kind of figure out what the equations would be to represent a situation like that. And that's really what today is all about. So let's go ahead and get started. A little bit of background knowledge, as we always do. Lately, we've been working on writing constant proportionality and unit rates and equations in both directions. One direction, which is the preferred way, remember, output over input, because that always gives us the constant of proportionality or the constant multiplier. And using those variables right there, we end up with an equation that is C equals 4B and a unit rate of $4 per book. Sometimes it makes sense to go the other direction, not so much in this one, because when we deal with input over output and we look at the unit rate, we end up with 1/4 of a book per dollar, and of course that makes absolutely no sense whatsoever. But sometimes we do want to go in the other direction. Okay? And of course $4 per book is the one that makes the most sense. And then we've added to that piece graphing, and of course this is proportional for the other reasons, but also because it is linear and goes through the origin. So let's start at number 1. Isaac earns $8 per hour at his job.
That's below minimum wage.
It is probably a little higher than that, right? So we could set up a table, and let's go ahead and do that. So if Isaac earns $8 per hour at his job when he has worked 0 hours, of course he has earned 0 money. At 1 hour, that's $8. And of course all of this we've done over and over and over again. This, of course, is a proportional relationship, because we have a constant multiplier, or what we will call next year a constant rate of change of $8 per hour. And we could check the ratios of output over input, and we would clearly see that those all simplify to 8. We could also utilize the ratios the other direction, which all simplify once again to the same thing, which in this case is 1/8, but there is one that makes more sense than the other. So ratios either direction are equivalent. That means it's a proportional relationship. The unit rate that makes the most sense in this one, of course, is $8 per hour. Let's fill that in. And I don't care which direction in your notes you put the ratios, but there is a spot for ratios. So can you please fill in the ratios? And since the preferred is typically output over input, let's just go with that one. So once again, our unit rate, which comes straight from the given sentence, $8 per hour. And the equation utilizing the unit rate that makes the most sense, if we use H and A, would be A equals 8H. That's simple. These are the things that we've been working on. And of course, the graph of that is very simple. We simply plot all of our ordered pairs and all of that stuff. So when we have an equation of a proportional relationship, that, in this case, that 8 right there, that is, of course, the numeric value of the unit rate. And that's going to be very important for these linear relationships that are not proportional. That is the numeric value of the unit rate. Okay? And then once again, our graph would look like this. But what if I take that graph right there and I look at it a little more carefully? Going between point and point, the graph shows us that for every $8 earned, he worked 1 hour. From here to here, since this is the amount earned axis, that's an increase of $8. Could you fill that in, please? And he worked 1 hour to accomplish that. If we keep kind of going up the ladder, if we want to think of it that way, from here to here is another $8. And he worked another hour. And we could keep going that way all the way up the graph. But the graph clearly shows us, thinking about it this way, that for every $8 that he earned, he worked 1 hour. I suppose you could think of it the reverse direction. For every hour he worked, he earned $8. That part right there is going to be huge with these linear relationships that are not proportional. That's another way of showing that that really is the unit rate. Okay? All right. So now, what if I take this graph and I do this to it? I move it up there. And you have that graph, by the way, in your notes. So what might that situation look like? Well, it might look like this. So now we're at number 2. Isaac currently has $5. He then earns $8 per hour at his job. So now I have a new table. So at 0 hours, how much does Isaac have? $5, right? We will end up calling that the initial value because that's how much he has at the very beginning before he starts working. Now he earns $8 per hour at his job. So after 1 hour of working, how much money does he have? Tell me, please. $13. Good. After 2 hours of work, how much does he now have? 21. And so on. Go ahead and finish off the table. And of course, that would be 3 hours, $29, 4 hours, $37, and so on. Okay? All right. So the ratios, if we were to check them, going with output over input. Now, we don't check the one 5 over 0 because that's undefined. 13 over 1 is 13. 21 over 2 is 21 over 2. Now, we really don't need to go any further. Why don't I need to go any further with the ratios? How come?
It's obviously not constant.
Yeah, they're obviously not the same. We don't have a constant rate of change, so we don't even need to go any further. That proves that this is not a proportional relationship, but we already kind of knew that, or we should have known that from the 0, 5. No matter which direction you check the ratios, they're not equivalent to each other, so that means this is not a proportional relationship. However, there might be an equation that can represent the scenario. Turn to your shoulder partner and see if you can come up with what that equation is. Annabella, what do you think it is?
A equals 8H plus 5.
Very good. Okay? So if we use H to represent the number of hours and A to represent the amount of money earned at that time, that would be 8. 8 equals 8H plus 5. Now, what's important about that is this. And we're going to pick and choose, or we're not going to pick and choose, but we're going to point out what parts are the important pieces here. So let's go back to this graph right here. The graph for this version of this problem still shows us that for every 8 hours earned, he worked 1 hour. So let me go to the graph. Just like the last time, there is an increase from here to here of $8, and you should write that in there, for 1 hour worked. And once again, we could go right up the ladder here. $8 for 1 hour worked. And $8 for 1 hour worked, and so on. I think you get the idea. So what that proves is that even though this is not proportional, we have an equation, but in addition to that, we do have a unit rate. Because after that initial value of $5, he continues to earn $8 per hour. So there's not a constant of proportionality, because it's not proportional, but there is a unit rate, and that graph proves it. So the unit rate is $8 per hour. Okay? I don't want you to think that because it's not proportional, we don't have a unit rate. We don't have a constant of proportionality, but we do have a unit rate. Now, we can also find that unit rate from just the equation alone. So I'm going to point this out, and you should add this to your notes. That number right there, just like with a proportional relationship, is the numeric value of the unit rate. Now, the only piece that we've added on there is this plus 5, and that plus 5 is always called the initial value. So let me define, and you need to add this somewhere in your notes. Let's define what the initial value is. The initial value is the value at the beginning of a situation or when the input is equal to 0. So at the beginning of this situation, Isaac had $5. That's the initial value. By the way, question for you. In problem number 1, what was the initial value? 0. Isaac didn't have anything at the very beginning, right? All proportional relationships, the initial value is 0. That's why we didn't even need to talk about it before. But now we do. Now we do. All right, so let's go to number 3. Number 3 states that Courtney is collecting coins. It says something about, and I'm holding off because I know a couple of you are still copying down the initial value thing. It says that she has 2 coins in her collection to start with and plans to add 4 coins each week. So I want you to do everything that we just did in number 2, except in number 2 was already graphed for you. So we're going to add the graph to that. So fill in the table, graph the scenario, find the equation, find the unit rate, find the initial value. Okay. All right, so Courtney is collecting coins. She has 2 coins in her collection to start. So at 0 weeks, she has 2 coins. And then she's adding 4 coins each week. And in terms of the graph, I went by 1s on the input axis. Don't forget to label what it means or what it represents. I went by 2s going up the output axis. And once again, when I walked around and looked, some of your graphs look slightly different, but that's just because you scaled differently than perhaps I did or perhaps your shoulder partner did. So doing scaling the way that I did, this is what your graph should look like. If we focus on the input situation here, we can have half of a week. So that, and we've talked about that before, so we do need to connect everything together. And so we draw our line through right there. We can clearly see it's linear, but it doesn't go through the origin, so therefore that's one reason why it's not a proportional relationship. We could check the ratios as well, but it's clearly not. All right, the equation of that would be using T and C. C equals 4T plus 2. Nobody seemed to have an issue with that. The unit rate, now once again, there is a unit rate here because we can see from the graph that when we increase by 4 coins right here, the amount of time that has passed is 1 week. 4 coins per week. That clearly shows us that we do, all the way up the ladder there, that we do have a unit rate. So the unit rate is 4 coins per week. The initial value, now once again, most of you wrote 2, but we've got to write down what it means within the meaning or the context of this problem. So what it means is that at 0 weeks, Courtney has 2 coins. Now there are lots of ways of phrasing that so that it means the same thing. You could also write that Courtney started with 2 coins, but you have to have something other than just a number, more than just a number. What does that initial value mean within the context of this problem? All right, let's go to number 4. Number 4, I filled out the table for you. So number 4, an airplane is at an elevation of 3,000 feet. The table below shows its elevation for every 2 miles that it travels. So its height in the sky compared to how many miles it travels. So go ahead and graph that. Make sure you scale your axes so that you can fit all of those ordered pairs on your graph. Make sure you label your input and output axes. Then make an attempt to find the unit rate, the equation, and the initial value. All right, so we plot our ordered pairs. I went by 1s on my miles axis. I went by 500s, essentially, 1,000 every 2 lines for my elevation axis. The 3,000 is clearly the initial value. That's where it started. And then we're decreasing that direction. And we can have half of a mile, so we should connect everything together. All right, first thing we're supposed to do is to find the equation. So we're starting at 3,000 feet, and we're decreasing, and I'm going to use y and x. I know some of you used other variables, and that's okay. You're starting at 3,000 feet, and you're decreasing 500 miles per, or 500 feet per mile, 500 feet per mile. You start at 3,000 feet, and you're decreasing at 500 feet per mile. Now, how do I know that? Well, I can look at my graph. I'm decreasing right here. That is clearly 500 feet. Because every line on the way that I scaled it is 500 feet for every 1 mile. Once again, right here, 500 feet for every 1 mile. Okay? So that is our unit rate, but we're decreasing, so the unit rate is actually negative. So this is the first time we've seen this. So the unit rate is, and I just showed you on the graph, it is negative 500 feet per mile. One of the very first things we started with at the beginning of the year was learning how to state integers in words. And one of them was a decrease in a something is represented by a negative number. A decrease of 500 feet per mile is negative 500 feet per mile. Okay? And then our initial value is, in the context of this problem, at 0 miles, the plane was at an elevation of 3,000 feet. There are lots of ways of saying the same thing, but whatever you write for your initial value, that's what it has to represent. Okay? Any questions about this one? All right, so let's move on. Now we're going to do some of the things we did yesterday, but with linear relationships that are not proportional. One of the things we worked on yesterday was graphing, but we graphed proportional relationships. Y equals 3x plus 3 is not proportional, but we can still easily graph it. So here we have, I'm giving you some input values of 0 through 4. So when x is 0 in this situation, what is y? Tell me, please. 3. Okay? And if you're not sure how we got that, 3x plus 3, if x is 0, which we're saying right here, I'm trying to change pen color here, we're saying right here x is 0. So if x is 0, we have 0 right there. And 3 times 0 is 0, and 0 plus 3 is 3. So y is 3. Okay? When x is 1, what is y? Tell me, please. 6. Good. And once again, the reason is because this time x is 1. So if we substitute, if we substitute 1 in for x, 3 times 1 is 3, 3 plus 3 is 6, and so on. And so if we keep going, when x is 2, y is 9. When x is 3, y is 12. When x is 4, y is 15. And so now, go ahead and plot all of those ordered pairs and draw your line through that. Okay, so here's what this graph should look like. I'm going by 1s on both axes. And so we plot our order pair 0, 3, 1, 6, 3, 12, 4, 15. Draw our line through. And I want to point out a couple of things here before I have you try the next one. All right? And that is this. This value, didn't mean to do that. This value right here, in all of the other problems, was the unit rate. That's the numeric value of it. This value right here is the numeric value of the initial value. And if we look at our graph, here is the initial value, and then on our graph, we are increasing 3 in the y direction for every 1 in the x direction. And once again, we could go up the ladder. 3 in the y direction for every 1 in the x direction. Now, I'm doing that because I'm also asking in this one, what is the unit rate and what is the initial value? So in this specific problem, the unit rate is, as I just showed you, 3 y's for each x. We have an increase in 3 y's for each 1 x. And the initial value is at x equals 0, y equals 3. Here we have y equals 14 minus 2x. When x is 0, y is 14. Remember, if x is 0, we are substituting 0 in for x right there. And 14 minus 0 is 14. And then we just keep substituting the new x value in there. Or we could see that there is a rate of change of negative 2. That's what the negative 2 is right there, that negative 2x. It's the unit rate. It's the numeric value of the unit rate. So we keep decreasing that value by 2. That's what that's all about. From there, we graph. Our graph should look like this. It should be decreasing because the unit rate is decreasing. That's what our graph should look like. The unit rate, once again, you can either find it right here or you can look on your graph. We are decreasing 2 y's for every 1x. Decreasing 2 y's for every 1x. All the way down our graph. And so that is what gives us our unit rate. So our unit rate is negative 2y for each 1x. And our initial value is when x is 0, y is equal to 14. Okay, any questions about number 6? All right, so now I'm going to give you a graph like this. Now we have to, like yesterday, we have to pay attention to what our input axis represents and what our output axis represents. In our input axis, it represents the number of hours. Our output axis represents the number of papers that have been graded. I'm just going to see if you can kind of figure out what that equation would be. Remember what we did yesterday is we had to find some perfect ordered pairs first, and then we went from there. So like yesterday, we needed to find some perfect ordered pairs first. One of them is 0, 6. Another one is 1, 12, and so on. So we fill in our table first. From there, we are supposed to find the unit rate. Lots of ways of doing that, but one, as I've been trying to show you on the graph, is as we increase right there 6 papers graded, as we increase 6 papers graded, that took 1 hour. That's one way of finding what the unit rate is. Now, if it wasn't simplified, you would need to simplify. But going all the way up our graph, 6 papers graded, and another 1 hour right there. So that tells us that our unit rate has to be 6 papers per hour. Now, once we have the unit rates, all we have to do is either look at the table or look at the graph for the initial value. The initial value is found right here and right there. So that should give us enough information to tell us what the equation is. It is y equals 6x plus 6. Okay? All right, do the same thing for number 8, and then we are finished for today. Number 8. It looks to me like most everybody's okay, except a few of you, it's the unit rate that was not quite right, and I'll show you why. But we have to find our perfect order pairs, and here they are. And then the first thing we need to do really is to find the unit rate. Well, this time you have to be a little more careful because if I look at the graph, I have a drop of 1,000 gallons. That's 1,000 gallons. How many seconds happen from there to there?
2 hours.
Or it's 2 hours, sorry. Yeah, that's 2 hours. So this is 1,000 gallons for every 2 hours. Not 1 hour. A drop of 1,000 gallons every 2 hours. That means the unit rate is actually negative 500, not a negative 1,000. So you have to be careful with that. Once again, here is a drop of 1,000 gallons, and it took 2 hours. Drop of 1,000 gallons, and it took 2 hours, and so on. And so what that means is that our unit rate is actually negative 500 gallons per hour. And our initial value, of course, is at 0 hours, the number of gallons was 10,000, and so that gives us an equation of y equals, or v equals in this case, because I did give you different variables, v equals 10,000 minus 500 T. Any questions? Okay, we are finished for today.